Welcome back to another episode of Heavy Wireless, part of the Pocket Pushers Podcast Network. My name is Keith Parsons, and today we're talking about UWB. I don't know. What is that? I was talking with some friends about this topic, and they said, oh, yeah, Cisco has ultra wideband, but that's not what we're going to be talking about. Today, I have with me Jeremy Baker and Scott McNeil, and we're going to be talking about ultra reliable. Jeremy, tell me, what is ultra reliable? What does it mean?
So the company was formerly Fluid Mesh, and then Cisco acquired them a few years ago. And basically, what it is a modified wireless that operates in the unlicensed frequency, but it does essentially MPLS over wireless. And so you can kind of think about it as like fiber or copper over the air, zero packet loss, zero latency. Very high availability, so you can run safety and stuff over it. So that's the ultra reliable wireless backhaul is what they call it now. We call it curb, but they fuss at us.
So how does it get that ultra reliability? I mean, fiber and wireless, I wouldn't even put them in the same bucket when it comes to the term reliability.
So the internals of the of the protocol, they use a protocol they call Prodigy, and essentially it has kind of a traffic cop on the network. They call it the conductor or the mesh end. And so what that does is builds a table of all the peer relations that are there. So there's a couple of different flavors of it, but in the mobility where you have roaming, the client can, send an update packet to the mesh end and then send a packet to the next device that it's communicating to. And then it just immediately takes over and all the peers know all of the routes to the mesh end.
So it's kind of a mesh, or it really is a mesh?
It's well, not necessarily like over the air, all disconnected. You can do like a wireless relay, but all of the access points have a data connection back to that mesh end device, and that could be a dedicated IPC, or you in some instances you could use one of the radios to basically maintain that the table. So I think it's the MBR table.
Well, let's back up and start it at the beginning. If you wanted to connect up, say a robot in a factory, and it needs to have that reliability, what components would you need to set up in that factory?
We pretty much have the same thing as like a traditional 802.11 setup. So starting from the network, you need kind of the traffic cop. So you'd have that mesh in device, which is, either the IPC or the radio. And then you would have your access points that are putting out 5 gigahertz wireless. So you'd have the same kind of coverage planning concerns. And then on the client side, you'd need a radio that can basically function as like a work group bridge across that. And then kind of the secret sauce in it is that the AP and the radios use up a passphrase and then, a transformation of the MAC addresses of the devices, which they call a mesh ID. And then they kind of establish their communication paths, and that's how they talk.
Yeah, so it's not like a distributed mesh where the individual radios are making up their mind. It's like some of your more involved industrial mesh technologies where you have that mesh coordinator, and that's what the mesh end is.
Yeah.
It's letting everybody know what their paths are, what they can transition to, and when to make that transition, which the result of that is virtually no packet loss on a radio to radio transition. And that's a huge deal.
But is it still using 802.11 and 5 gig, or some proprietary protocol?
It's using the 5 gig frequency, so it's the unlicensed frequency, but it's sort of a modified, like you could still capture the frames with like a monitor mode NIC or even an AP sniffing on that channel. But the difference is that the packets are different. So there's no beacons, there's no probes or anything like that. You have kind of your shared passphrase. If you have AES encryption, all the devices have to have that enabled, and then they just have to be on the same frequency to establish a communication relationship.
And before it was Cisco, when it was Fluid Mesh, while they used the standard unlicensed frequencies, they did everything based upon actual frequency designation as opposed to the 802.11 channel structure. And that was something that changed when Fluid Mesh became Cisco, as they changed up how they're broadcasting, and as opposed to doing individual frequencies before, they moved over to the 802.11 channel structure while still using their Prodigy protocol.
Microtech had the same. In fact, even today, when you go to Microtech, you configure a AP channel by its frequency, not by its
Right.
normal number.
Yeah, it's been a while since I've been in Microtech, but same concept.
Do they use, well, now that it's with Cisco, are they using the same size channels, 20, 40s, 80s?
Yes.
And if you can decode the frames, obviously it's 802.11 protocol because Wireshark knows how to decode those.
Well, no, you have to, the company I work for has written some Lewis, so you can do that, but there's some documentation online you can write. You could write like a parser for it. So it's, you get like a data structure and then in that byte array, depending on what they're called TLSs, but depending on what telemetry aspect you're looking at, that information's is in there in like some sort of a byte offset.
My 802.11 radio can hear it, but I need that specific, it's called a dissector in Wireshark to figure out what's going on. Okay.
I wouldn't say your 802.11 radio could hear it. Your 802.11 radio is going to just see it as noise because it doesn't have the beacons and the other frame structure.
Oh, okay. So
Well, if it was capturing on monitor mode, it could potentially do it. But yeah, it's not going to detect it as 802.11 traffic.
Since we don't have beacons and probes and all our favorite little frame captures and how they go back and forth in 802.11, what's the process of how a client joins this mesh network, sends traffic, knows it's his turn to talk?
So that's I guess in the details of it, when they come on, there's some sort of telemetry packets that they exchange between them. I wouldn't be able to give you a rock solid technical explanation of it, but basically like they detect that there's something out there in that mesh ID, and it's probably something similar to a probe frame, a probe request from the client side, and then a beacon on the other side. It'll send out a packet that says, "Hey, I'm mesh ID, whatever."
So if you were configuring this setup, what would the process be?
Well, now they just released a thing where you should be able to do it through the 9800 controller with the new software release. But typically you would, take like your DHCP server, assign an IP address to it, and then either through CLI or web configurator, you'd assign the IP address. And then really like the basics for making a connection between the two of them is you enter that shared passphrase. So I like to think of it as kind of a combination of SSID and passphrase, and then you put them on the same frequency. And then also, like if you're doing anything like VLANs or anything like that, you enable all that stuff in the radio. And then when you power them on, in some kind of way, they have some transmission where they detect each other, and then they'll establish a communication if those interlocks are met.
You'd mentioned that its big claim to fame is that it's ultra reliable. I mean, it's in its name. Does that mean there's multiple copies of those frames? So if one has, I mean, we know in the wireless world, RF is sometimes pretty messy. So how does it guarantee that it gets one if one of the radio channels is out? Is there like multiple frequencies it uses?
So that depends, right? Typically it's deployed as like a single band application. So they're all on the same frequency. You can have frequency scanning and stuff if you want to like do fleet splitting and things like that. But if you want to increase the reliability, they have a protocol called MPO, multipath operations. And so what that is I think about it like PRP on like a wired network. So the frames are duplicated and then they're sent out of all broadcast interfaces and then picked up, and then it's first past the gate. So you can do frequency separation, you can do different antenna locations on vehicles and stuff like that to kind of give yourself a little bit more robust likelihood of receiving the packets.
And to take that one step further, each chassis actually has two radios in it. So they're monitoring multiple paths. And at any one point, they can switch radios on whatever's going to have the more desirable path. And because it's hardware switching internal to the chassis, there's no loss.
And even, Scott, and even kind of in the old school fluid mesh days, you could chain. I mean, we've had some applications with 5 or 6 client radios on them, either operating on the same frequency or, like an ABC frequency. So then they're talking and they'll coordinate themselves on the wired segment of the vehicle, and even some of the newer things. Because if you get in a cramped down space where the RF projection, the over air transmission distance isn't really the issue, but it's congestion in there. We'll do things where we'll split a fleet of vehicles with, 1 through 20s on A, and then 21 through 40s on B, as far as like a frequency wise.
What kind of benefits in addition to reliability? A lot of people now are talking about, like moving to 5G because it has really low latency. Is this also giving you that same kind of latency?
Yeah, so
Absolutely.
they say it's they say 0 millisecond, but it's sub millisecond latency typically. And then it just depends on what's on the wired infrastructure and on the vehicle switching side. That'll kind of hose you up.
And then, so you mentioned capacity. Is there some capacity sweet spot where more than X number of devices? You mentioned splitting into different groups.
So that'll kind of depend on the actual throughput coming off of the vehicles. So if you have obviously if you have 100 milliseconds before your vehicle faults or something like that, if you have too many connections trying to talk simultaneously, it's still it's still contention based. So that would be a motivator for that, but it just depends on kind of how much data you're transferring across it.
Well, we've all heard the good, fast, cheap, choose two. So high reliability, low latency, high throughput.
Well,
Which one
I
has to
don't know if
go?
it'd be. You're definitely not. I don't think you're getting cheap anywhere in there.
No, you're not going to get cheap
Um,
in there.
Especially the more reliable that you want to get if you're trying to run any kind of high availability controls or anything on there. Then you get into stuff where you have to go in and mess with A and PDU buffers and make it where it's not aggregating frames. You have to mess with the COS settings and stuff like that, and then you have to actually tag the traffic going into the radio to make sure that it carries across.
Well, I don't want to be in salesman mode, but if you were comparing this to a 802.11 solution with a worker wireless bridge as the endpoint, with just regular Wi-Fi APs, what's the upcharge to move to this ultra reliable mode?
Scott, do you have a good idea on that? I'm trying to think.
The APs themselves individually are fairly pricey, but in my personal opinion, if you're looking at standard bridging and you don't need any sort of high-speed mobility, it's not exactly going to be the best price-wise fit for that when you can use, there's a ton of different lesser expensive 802.11 solutions for point-to-point, point-to-multipoint. But where Curb really shines is in mobility because of their MPO, because of, and something we didn't even touch on is their protocols of fluid max and fluidity, and how they use those protocols to control everything. One of the primary use cases for Curb in general is high speed rail. So they supply and really in Europe, like all over Europe, they supply wireless internet access to high speed rail. And from, if I remember correctly, they can seamlessly integrate wireless connectivity to trains up to 300 mile an hour, in constant motion. And that's, again, that's where these radios really shine, is in that super high speed radio to radio transitioning environment. Um, like I said, the pricing on them, they're not cheap radios. So you're not going to go, go to your distributor and say, hey, give me a $600 or $800 or $1,000 radio. I mean, these guys are very proud of their technology. So,
Yes.
if you're looking retail, you're probably looking at 3K a piece retail, before any sort of like vendor discounts.
From the client
Yeah,
side
and
or the
then
AP side?
so it depends. Well, the all of the radios can either be like an access point type radio or a client type radio.
They don't
And
really have them
so
designed as specific clients versus specific APs.
if you have let's just say like the lower IP rated radio that's meant for like a control cabinet or an enclosure, it's probably around you know, finger in there, it's probably around $1,500. And then not where they get you, but where they kind of piece you in is the licensing is, if you need 5 megs or 500K of throughput, if you don't need much throughput, you can do essentials, and then it goes 50, and then the next tier up, like the top tier, is the theoretical maximum, and then that advantage and premier licensing also opens up that MPO. So then if you need the additional redundancy, and then that, and that can be as much as the radio, depending on your discounting and stuff. So you're, realistically, I would say, finger in the air, you're at least $5,000 a radio with licensing and
Yeah,
everything.
I wasn't considering licensing. Yeah,
Yeah,
you're absolutely right.
That makes you sit back and go, "Oh, I have to really, really want it." But there are cases where there's definite need for that low latency, high mobility, and reliability all at the same time.
absolutely.
I like your example of trains, but I can think of uh, robotically controlled devices in many manufacturing environments that just have to be connected.
Yeah, we're
Paper mill wood yards is a prime example. In their chip yards for these giant machines, they move back and forth, maybe 1,000 feet, and all they're doing is stacking and reclaiming wood chips. But they're constant in motion. They're not super fast, but they're constant in motion, and that is the beginning of the paper making process. And so if that feed is not continuous and measured constantly, the entire process stops. And so that transition and that reliability is very important in that kind of scenario. And I would say that would be slow speed rail, not high speed rail.
I've worked on some large places like that, and the vendor who sells those machines offers an umbilical. I mean, they have to have power. They have to have. In fact, I've been in some Coney cranes that have water for where the employee's sitting doing work. So the umbilical even has water in it. And they offer an umbilical with fiber, and the customers are like, "Oh no, no, we'll use wireless instead."
well, the problem with those is that you might be able to get that same power umbilical cable for, $10,000-15,000 without that data in it. And if you need the fiber stuff in it, the cable can go to 60 or $80,000, and if it breaks, you've got a 2-3 month lead time to get it. So we've seen a lot of people going from stuff like that to sort of bypass that.
My my initial is I like fiber better than copper, better than point to point, better than point to multi point, and the worst thing on the list is mesh. And so when this started out with mesh, I'm like, oh, but it does fix problems that other things have. Fiber umbilicals, when they break, you're right, that is a huge undertaking to get it fixed. So, what other possible scenarios can you see this making financial sense?
Well, I think if we've all been in sort of manufacturing environments, and so I think the real easy thing to do is just, what is your company's downtime cost? We have some customers that, a minute or two of downtime is $100,000, and then that, 50% boost on what the normal price would be gets really cheap really quick.
It's all about risk mitigation, right? You want the risk of that downtime being as low as humanly possible, and if that costs you more than another solution, but it drops that risk significantly, then it becomes worth it.
Yeah, and Keith, another thing, not necessarily price wise, but we use this in entertainment as well. And so if you're putting somebody's kid on a vehicle and sending it off, it's you can't really put a price tag on the thing stopping when it's supposed to stop either.
Definitely. When you look at the bigger picture, price isn't always an answer. If you were going to go into a site, is this something you would think about the design like a Wi-Fi design? As in, it's using 5 gigahertz. Do we have to follow all the same 5 gigahertz distances, or is there better antennas that can be used here?
It's been essentially the same. They're
Yeah.
not they're not reinventing the wheel as far as the 5 gigahertz broadcast. You're still at the same physical limitations of the frequency that you have with everything else.
Yeah, and so Cisco's got some dedicated antennas that are approved for use of it, and then occasionally we'll use some third-party ones in there. You can still, your Hamina, Ekahau, Cytos, any of those, you can use those for the planning stuff of it. What's a little bit tricky is the validation side of it because you can't use your Sidekick or your Nomad
Or your Wi-Fi
to
explorers
yeah,
or your standard
or your
Wi-Fi
or your
scanners. Yeah.
or
Because
your
they
air
just don't
check.
see it.
Well,
Um,
let's lift up the stack instead of down the stack. And from an IP standpoint, does this just look like another Ethernet cable? I mean, if you're replacing one connection, would it look just like there was an Ethernet bridge in between?
It's just transparent. It's transparent to the data.
So nothing special there. The end client device just pulls an IP through whatever VLAN it's on and just works normal.
Well, I mean, typically in my universe, we statically assign everything, but yeah, it's as far as the data is concerned, it's a transparent bridge.
Well, thanks for your time today, guys, learning about Curb or Ultra Reliable. And how would someone track you guys down? And by the way, give us a little shout out for your podcast.
Well, I'm a LinkedIn junkie, so you can find me at Scott McNeil on LinkedIn. And I am on Twitter X a little bit here and there, but between LinkedIn and then the our podcast, the Industrial Wi-Fi Shop, everything that I put there on the site to support the show.
yeah, that's right. I have an X account. I haven't logged into it or looked at it in 6 months, though. Seems like the traffic's not too good there. I'm in the WLAN Pro Slack. If anybody's looking for me there, is Jerms Baker or Jerms A Baker. I'm on LinkedIn as well, Jeremy Baker. Or you could look at for Industrial Wi-Fi Shop on LinkedIn, and you should be able to find us that way as well.
Well, thanks for your time today. And we will put in the show notes both your individual LinkedIn accounts, and they have an Industrial Wi-Fi Shop podcast. I highly recommend listening into that. You've been listening to another episode of Heavy Wireless, part of the Packet Pushers Podcast Network. My name is Keith Parsons, and we look forward to talking to you in the next episode.